We had a little bit of homework last night. Gave you a problem where we had three objects and a rope joining those three objects together, pulling it to the right with 100 newtons friction acting on all of the objects. And we were asked to find something that we were only asked to find yesterday for the first time, and that is a tension in a rope that joins two of them together. Now, you saw yesterday that this isn't really any harder than the other one-dimensional problems that we've encountered to this point. It's just twice as much work, because you got to do that whole net force is equal to the sum of the forces twice. Now, you see this question. The very first thing that we're going to do, of course, is pretend we've got one object. Those three objects are three objects inside of a big box. It's the three jugs of ice cream or the three containers of ice cream inside the big truck. We're analyzing the big truck right now. So the big truck is going to look like this with a single force acting to the right on that truck of 100 newtons and a single force of friction, or you could think of it as three forces of friction if you want, acting to the left, totaling 80 newtons. Let's analyze that, the entire system, if you want to think of it as the truck, that works. Analyze the entire system and find the acceleration of that system, thereby finding the acceleration of the individual objects within that system. So let's say F net is equal to the sum of the forces. That's going to be FF1 plus FF2 plus FF3. Again, first thing, we always want to find that acceleration. Sometimes you're given the acceleration already. If you are, that's great. Skip this first step. That's a big help, actually. A lot less work. Cuts the work in half. If the net force is equal to all of these forces added together, then MA is equal to all of those forces. What mass would I use there? 10, 20, 10, or some kind of combination of them? 20 minus 10 is 0. Use a mass of 0, right? Tyler, what mass do I use? 40, yeah. We're going to add them up. So total mass of 40. Don't know the acceleration. FF1 is neg 20 plus neg 40 plus neg 20 plus 100. I believe that gives me an acceleration of 0.5, isn't it? 0.50 meters per second squared. All right, how many people got that? Good. Good. Okay, that's the first step. You're halfway through here now. Now it's the other half of the problem where you got to pick one object and analyze one object. Remember what I said yesterday? You want to pick an object on the end, either object 1 or object 3. You don't want to pick object 2. And the reason we don't want to pick object number 2 is because object 2 has 2 ropes pulling on it, and we don't know what either of those forces are. So generally, you want to stay away from picking objects in the middle. Pick one of them at the end. Now, which one makes sense to pick, 1 or 3? What? Since you're trying to find the force of the rope between 1 and 2, you want to pick object number 1. So let's draw a free body diagram for object number 1. Object number 1 is being pulled to the left with a force of friction, FF1, that's 20 newtons, and it's being pulled to the right with a force of tension in the rope. That's it. There is gravity and normal force, but they cancel. Horizontally, these are the only forces that act. Now, let's analyze this the same way as we analyzed the last step, FF1 plus FT. What mass do I use here? 10, 20, 10, combination of them, 40, 10. Use the total mass, but total mass of the system that we're analyzing here. Acceleration is 0.50. FF1 is 20 newtons. We're going to make it negative because it's to the left. 10 times 0.5 is 5. Plus 20 gives me, I think, 25 newtons, isn't it? How many people got that? Good. Excellent. Now, I didn't ask you to do this, but what if I asked you to find this force, the force between 2 and 3? Would we have to do the first step over again? Would we have to do this blue step over again? No, because we already have the acceleration. That's what we want to find first. It's the acceleration of object 1, 2, and 3, all of them. So we wouldn't have to do that again. When we go to do this step in analyzing an individual object, which object would you likely pick to analyze? Probably not number 1, because we just did that, right? 2 or 3? Probably 3. Although in that case, you could analyze number 2, because remember, in this case, you've already found the force of this rope, right? Does that make sense how that would work in this case? Now, you find the force of that rope. If you were analyzing number 2, it wouldn't be 25 newtons. It would be close, but it's not 25. If you're analyzing object number 1, it's 25 newtons. If you're analyzing object 2, it would be negative 25 newtons. Object A applies a force on B. B applies an equal and opposite force on A. Okay? Got it? I was actually surprised at how many people got that correct. Are we okay with that, or do we need to do another example? If I was to give you a quiz on that one, I probably won't give you a quiz tomorrow because it's 2 days in a row here now. But if I was to give you a quiz first of the week, would you guys nail that? Yeah? Okay. I won't give you another example then. I guess we're good with that. We're going to jump forward a little bit here now, shift gears somewhat, and talk a little bit less about forces, although forces are going to certainly come into play here over the next week. But our focus is not going to be on force so much, but rather our focus is going to be on energy. Energy is the ability to do work. The ability to do something. Energy is kind of it's kind of a weird concept because you can't feel it, you can't touch it, you can't see it. It's almost like we made it up to explain something that just does something. Energy is the ability to do work. Now, energy isn't necessarily doing work at any given time. It can be, but it isn't necessarily doing work at any given time. Energy can be doing work, or it may be kind of just stored to do work later. If it's doing work right now, then we call it kinetic energy. Kinetic energy is the energy of motion. If something's moving, it's doing work now. That's kinetic energy. Versus potential energy, which is stored energy. It's not doing anything right now, but if harnessed, has the potential to do something, has the ability to do work down the road. Kinetic energy, we don't really differentiate between different kinds of kinetic energy. If it's moving, it's got kinetic energy. Done. But potential energy, we do differentiate. There's lots of different kinds of potential energy, lots of different categories or classifications of potential energy, stored energy. Can you give me one? You guys have seen this before a little bit in Science 10, even a little bit before that. What's one kind of stored energy? What's one way that we can keep energy, not using it right now, not doing work right now, but storing it to do work later on? Joseph? Good. Chemical potential energy would be a good example of stored energy. Where would you see chemical potential energy? Give me one place you'd see it. Good. In a battery, there's, we've got to be careful with that, but you're absolutely right. In a battery, there's chemical potential energy stored, which gets converted to electric energy, which is also a form of potential energy. So we'll write that down as well. But as it's just stored in the battery, it is chemical potential. Which electric potential energy can be converted ultimately to kinetic energy, in a toy car as the car moves, whatever. Where's another place that you see chemical potential energy being used? Yep. Fire, yes, in the sense of the fuel, yes. The fuel for the fire has chemical potential energy stored in it, yes. Now, as it released and becomes heat, thermal energy would be a form of kinetic energy because we're talking about particles bouncing around as something gets hot, right? But as the fuel, yes. Speaking of fuel, the fuel in your car is chemical potential energy, right? Of course, it's not doing anything right now, but it has the potential to do something as the car drives down the road, it's chemical potential energy having been converted to kinetic energy. It's funny how we miss the obvious, though, eh? Like there's one that's staring us right in the face. Not only is it staring us right in the face, it's right in the face. A glow stick, okay. That's not the one that's actually literally staring me in the face right now, but you're absolutely correct. The glow stick. Do you guys know how a glow stick works? There's two chemicals in a glow stick. They're separated. There's a little glass tube inside the glow stick with one chemical, and then it's in a bath of another chemical. And the idea is you break that little glass tube. And you do that by just bending the glow stick. Right? You break the little glass tube, and it mixes the two chemicals. It's an exothermic chemical reaction, which releases light energy. Right? So those two chemicals have potential energy, chemical potential energy stored in them. Turns it into light energy. Or if you have a hot pack, same kind of idea, right? Hot pack, chemicals mix and turns it into thermal energy, right? What about us? What about our bodies, right? You have chemical potential energy stored in your body. How do you move? Hey, how do you run? How do you play sports? How do you think? How do you write? A chemical potential energy stored in our bodies, which gets converted sometimes several times through several transformations, ultimately into kinetic energy as it does something, right? As you write notes with your pen and your hand is moving, or you run across the soccer field, or whatever the case may be, potential converted to kinetic. All right, let's see if we can identify another kind of potential energy here. We could call solar one. A little bit different, but solar energy isn't really doing anything right now, right? But it has the potential to do something. Sure. No, photosynthesis wouldn't be a type of energy. It's a process. But in the end, photosynthesis involves converting light and water to sugar. Okay, so ultimately, you do have an energy transformation taking place within photosynthesis. It would be light energy converted to chemical potential energy, right? So it's kind of one form of potential energy converted to another. So there is potential energy involved there at a couple levels, but photosynthesis itself is the process as opposed to. It'd be kind of analogous to saying, look, in your car, there's gasoline. There's chemical potential energy stored in the gasoline. The process of converting it means putting your foot on the gas pedal. That's not energy. That's the process of converting it. Okay, that's analogous to photosynthesis. Yep. Geothermal. That's a good one. Nobody's ever said that when I've listed this. Geothermal. What would that be? In a sense, you want to think of it as potential, right? Because it's not doing anything right now. But no, I'd actually classify geothermal, I think, as kinetic because it's heat, right? It's hot water, basically. So yeah, I think I'd classify that as kinetic energy. Yeah. Going back to chemical for a second, do you guys know how we generate statistics about 10 years ago were about 80%. I'm not sure if it's quite that high now, but going to be fairly close, I think. How we generate about 80%-ish of our electricity in Alberta? Coal. We burn coal, which is horribly dirty. It's about the dirtiest thing we can possibly burn, which, by the way, actually releases radioactive material in the process. We think, oh, coal's dirty, but at least it's not nuclear, right? At least we're not, at least we don't have this nuclear waste. Well, it actually releases as much radioactive material as you get produced from nuclear power plants. It doesn't last as long. It's not quite as dangerous, but it still releases all kinds of bad stuff. Coal's terrible. Chemical potential energy stored in coal as well, right? How else do we generate electricity in Alberta, though? Yeah, we use quite a bit of wind, although that's still a relatively low percentage. okay, because each of the individual turbines, uh, is rather insignificant in the grand scheme of things. Okay, wind would be a kinetic energy, right? Because it's movement. How else though? Natural. Somebody said gas. Like we burn natural gas. We burn quite a bit of natural gas. Same idea as coal, except it's a lot cleaner. Chemical potential energy again. Hydro. I'm not sure how much hydroelectricity we have in Alberta, although we do have some, I think. We dam up rivers, and you got a little trickle of a river flowing, and then what happens? We stick this big dam in front of it. Why is the bottom of the dam thicker, by the way, than the top? The amount of pressure at the bottom of the lake is way higher than the amount of pressure at the top, right? Because you've got a lot more water pushing down. It has to be stronger at the bottom than it does at the top. So you dam up this river, okay, that was flowing like this, and all of a sudden this side of the river the level goes down, and this side of the river, the level goes up. So this river that was flowing over here isn't a river anymore, it's a lake. What happens to that water? Flows down through this penstock, turns a turbine, generates electricity, water comes out the other side. Okay, so you're generating electricity. Where did that energy come from? The water falling, right? The water falling was kinetic energy. Well, how did the water fall? It had potential energy to start off. What kind of potential energy? Somebody said it. Gravitational potential energy. Gravitational potential energy. We're going to focus quite a bit over the next week on gravitational potential energy, actually. How else is electricity generated? Not in Alberta. In Ontario, there's a lot of it generated this way. In the United States, there's a ton of it generated this way. Some in New Brunswick as well. One of these in New Brunswick. No, that's not what I'm talking about, but solar farms, that Alberta would actually be one of the prime spots to build a solar farm. We actually get more sunlight in Alberta than most parts of North America, most if not all parts of North America. And we think, because it's so north, it's not a very good spot. That's why we actually have, you look around Okotoks and around Calgary, there's actually quite a few people with solar panels on the roof. Not all solar electricity panels, many of them are solar heating panels, but the reason we do that is because we get a lot of direct sunlight. We get a lot. So southern Alberta would be a good place to put a solar farm. That's not what I'm talking about. Okay, the production of electricity by solar power, thus far at least, it seems to be most efficient if we're doing it on a smaller scale, like put it on your roof, as opposed to make a big farm and transmit it to you, right? Do it locally, kind of thing. Sorry? Yeah, basically, yeah. The other kind that I'm thinking of is nuclear power. There's a fair bit of nuclear power in Ontario, as I said, a ton of nuclear power in the United States, a little bit in New Brunswick. I'm not sure about other provinces. In the end, that's the energy that's stored in the nucleus of an atom. Okay, the energy that's stored in the nucleus of the atom. When you split that atom, then the energy is released, and there's a lot of it released. Do you know though that in the end, how the electricity is generated in all of these cases, with the exception of solar? This is what they all have in common. A turbine turns. When you burn coal, it doesn't generate electricity right away. It generates heat. What does that heat do? It boils water. When water boils, it turns into steam, and steam rises. And when the steam rises, it turns a turbine and generates electricity. When you have hydroelectric power, gravitational potential energy is converted to kinetic as the water falls, and the falling water turns a turbine and generates electricity. When you have nuclear power, you don't generate electricity from the nucleus of an atom, you generate heat. What does that heat do? It boils water, and that boiling water turns into steam, and steam rises, and it turns a turbine, and it generates electricity, just like coal, except it does it a lot more efficiently than coal does. You get a lot more out of it than coal, but it's the same basic process of generating electricity. There's one more kind that I'm thinking of, but I'm not sure that you guys are going to come up with this one. You've all seen it. In fact, you've seen it more than you've seen solar or nuclear. So I take a hair elastic, hold it up, stretch it, hold it up near Tyler, and he kind of cringes a little bit. Why are you scared? Think I'm going to hit you with the elastic? Elastic going to hurt? No? No, but you cringed. Because you think it's going to sting when it hits you, right, when I let it go. Why is it going to sting? Because it has kinetic energy when it's moving, right? Where did it get kinetic energy from? When I stretched it, it's got potential energy in it, right? Stored energy. We call it elastic potential energy. So another kind of potential energy will be elastic. That's one that we're going to talk about a fair bit as well. Elastic potential energy. Similar kind we could call spring potential energy in a stretched spring. Same kind of idea there. Spring or elastic potential energy. All right. Kinetic energy, we said, really we don't differentiate between different kinds of kinetic energy, although, there is thermal energy and, lots of different examples of kinetic energy. Generally, we just say kinetic energy can be described by one simple equation, and that is EK is equal to, you've seen this. You know it now? EK is equal to 1/2 mv squared. Do you remember that from Science 10? No? Oh, you've done kinetic energy in Science 10. I know you have. Years ago, I used to teach Science 10. I know it's there. What does M stand for? Mass. And it's going to be measured in kilograms. What does V stand for? Oh, she got it right. Ilna said speed. I was expecting you to say velocity. It's not velocity, it's speed. Kinetic energy does not depend in the slightest on direction. So it's not 1/2 m times velocity squared, it's 1/2 m times speed squared, speed in meters per second. EK, of course, is the kinetic energy. Do you know what units kinetic energy would be measured in? Somebody said it. Joules. Measured in joules. Now, mass is a scalar. Speed is a scalar. Kinetic energy would be a scalar times a scalar squared is a scalar. So basically we're saying you launch that little clothespin bullet, hits somebody, it hurts. It doesn't matter which way it was moving. It hurts the same amount. Kinetic energy is a scalar. It hurts because the kinetic energy of this little clothespin bullet. It doesn't hurt because it was moving to the right. It hurts because it was moving. Make sense? All right. I circled two kinds of potential energy. We're going to focus on those two kinds. You'll do chemical energy in chemistry probably. We'll do electric energy in physics 30. Solar energy we probably won't touch in high school. Nuclear, we won't. We'll do a little bit of nuclear energy in physics 30 as well, a little bit. But we're going to focus this year, at least, in this class, on gravitational potential energy and elastic potential energy. Gravitational potential energy is given by the equation EP is, you've seen this before in Science 10. Come on, you guys. MGH, good. EP is MGH. Means the heavier something is, the more potential it has to do damage when it hits the ground, right? You drop a feather, you drop a hammer. Which one's going to hurt more when it hits you? The hammer, because it has more potential energy, and therefore it will have more kinetic energy when it hits you. M is the mass, and it's going to be measured in kilograms. G is 9.81 meters per second squared, at least if we're on the surface of the Earth. H is the height, and it's going to be measured in meters. Okay. Bigger M is, the bigger G is. If you went to another planet where Jupiter, where it's maybe 24 meters per second squared. H is height, bigger H is. All three of these variables increase them somehow. Okay. The amount of potential energy is going to be higher. Therefore, kinetic energy eventually will be higher as well. EP is the potential energy. Gravitational potential energy. The units would be joules. And just like with kinetic energy, it's a scalar, because all forms of energy are scalars. Finally, elastic potential energy. You've never seen this one before, so I'll just give it to you. EP is equal to 1/2 kx squared. EP is the elastic potential energy, and it's measured in joules as well. It's a scalar as well. K is known as the spring constant, or the elastic constant. It's basically a measure of the stiffness of the spring or elastic. You take the spring out of a pen, and it's not a very stiff spring, right? It can hold energy, but can't hold a ton of energy because K is a small number. But if you take the spring off the back of your car, you guys know what I'm talking about? The spring that's around the strut or the shock or whatever it is. I don't know much about cars, but it's really, really stiff, and it can hold a lot of potential energy. Okay, the stiffer the spring is generally, the higher the spring constant, or the spring or elastic constant. Its units, newtons per meter. We'll talk more over the next several days as to how we might find that value of spring constant. Finally, X is the displacement of the spring in meters. But I want you to be careful here. It's not the displacement that you're typically thinking of. Can I borrow that elastic again? Thank you. The displacement that you usually think of is this displacement. The movement of the elastic, right? How far the elastic traveled. This displacement that we're talking about is how much the elastic is stretched or compressed. So I can throw it across the room and the displacement might be 5 meters. But that's not X displacement, that's delta D displacement. X displacement is the 5 centimeters I just stretched that elastic or compressed a spring. Does that make sense? So same variable, it's called the same thing, but it means something slightly different. Make sense? All right. We'll wrap it up there for today. We'll pick it up tomorrow with a few calculations involving kinetic and potential energy, all right?